Hi, I'm Xueqian. I'll present PointNetLK Revisited, a generalized registration method. This work is done with Johnny and Simon at Argo AI. Imagine a situation where you want to align two point clouds, while these point clouds are statistically different from the training dataset. For example, they're from unseen object categories, unknown depth sensors, or different complex things. In these circumstances, the common strategy is to rely on classical non-learning methods whose performance is inferior to learning-based methods but can generalize well to unknown conditions. In this work, we revisited PointNetLK, which combines learning-based feature representation and classical Lucas-Canale algorithm. We demonstrate how a simple modification can greatly affect the alignment of complex real-world things by training solely on clean, dense, synthetic objects. The registration problem is to find the rigid transformation that aligns two-point clouds. In our approach, the objective is to solve for C that minimizes the feature difference between the source point cloud PS and the template point cloud PT. Instead of directly solving for C, we iteratively solve for increment delta C. The left figure shows the point cloud registration with iterations. With 7 iterations, we find the final registration result. The most important part of our approach is to compute the Jacobian matrix. In the original PointNetLK, the authors numerically approximated Jacobian J using finite differences with step size Tp. However, it is numerically unstable with a step size choice. It can result in biased gradient values with a large step size or catastrophic cancellation with a small step size. We propose to compute a decomposable analytical Jacobian, which circumvents the above issue. Our analytical Jacobian can decompose into two parts, feature gradient and warp Jacobian. With k as feature size, n as the number of points in a point cloud, the feature gradient is a k/3 matrix that describes how the point feature embedding phi pt changes with respect to pt. Warp Jacobian is a 3n/p matrix that describes how changes in the parameters C affect the transformation of pt. P is the number of parameters. But why decomposition is important? Because we can simply replace the warp Jacobian during testing to perform different registration tasks. For example, fewer parameters, such as 3D translation, or more parameters, such as non-rigid transformation. Or one can compose another warp Jacobian, such as a conditional Jacobian, like we did for Volcanization. Here we show some registration results on the synthetic dataset ModelNet40 and Stanford 3D scans. Our method preserves high fidelity, robustness, and generalizability of noisy data, sparse data, and data captured from different depth sensors. But how can we apply our approach to the real-world things? Our solution is voxelization. Here we show an illustration in 2D. Given a large-scale complex thing, we voxelize the space into several subspaces that exclude the voxels with fewer points and only use voxels with a certain number of points. This voxels is denoted as VM. We use a single point net to extract the feature find VM from points within VM, then compute the Jacobian JVM for each voxel. Finally, we collect all JVM and compose a conditioned warp Jacobian to get the final global Jacobian JG for the entire thing. Here we show several registration results on real-world indoor dataset 3D March. The green denotes target, while purple is a registered point cloud. With a decomposable Jacobian, we only need to do voxelization during testing. Please note that the feature gradients are learned from the synthetic ModelNet40 dataset, and only by replacing the warp Jacobian can we do registration on complex real-world things. We first demonstrate registration results on the real-world outdoor dataset Kitty. The left figure shows that within 10 iterations, our method finds the best alignment. Again, the model is trained on a synthetic dataset.